Hello, everybody. Welcome to today's webinar, Low Speed Pre-Ignition Update. I am Amanda Harmoning. I'm an admin assistant here at AERA, and I will be moderating today's webinar. And also with me from AERA is Rob Monroe.
Hello, everyone. My name's Rob Monroe. I look after membership and technical development here at AERA, and I want to welcome you to today's webinar with Lake Speed Junior. So just a couple quick housekeeping slides before we get started. For those of you who don't know who we are, AERA is a nonprofit association that started back in 1922. So our main focus is to supply engine builders with technical specifications and information, as well as we like to create networking opportunities for our members to learn from each other, just like what we're doing today. So our goal is that after today's webinar, you'll be able to take what you've learned back to the shop or to the business after what Lake goes through with you, and apply that right away to what you're doing. So that's what we do here at AERA. And today's webinar, we are very, very lucky. This presenter is a huge asset to our industry. He's got a background in competitive racing, and he actually grew up in a family business of racing. Lake Speed Junior spends most of his time, we're lucky, he educates us on lubrication technology, and as a certified lubrication specialist, he is the main man at Driven Racing Oil. So let me welcome Lake Speed Junior. And hey, Lake, how's it going today?
Doing good, Rob. Thank you, sir. Okay, we can get going. So we actually skip a whole slide right here because Rob just basically filled everybody in. I said, I am Lake Speed Junior. My dad's Lake Speed Senior, and that picture right there, he's the guy in the blue helmet. He's only behind me briefly, as I can show in the next picture here. So just anybody's curious and wants to know how Dad is. So Dad's 71 years old. This is me and him last year, last August actually, at Camden Raceway in Ohio. And you see up there on the speeds, the Dad won the 135cc Sidewinder class. I finished second. His best time was 35.633 seconds, and I was 35.82. So he's still a couple of tenths faster than me, even at 71. Now, the interesting thing about this isn't just that Dad's fast and he's still better than me, which I've known that my whole life, by the way, that there's about 13 classes in that race. 6 of them were twin engine classes. This is a single Sidewinder. So we ran a 35.66 or 63 in a single engine go-kart. And there was guys out there on twin engine go-karts that were not running faster than 35.633. In fact, Dad was, both of us actually outran all the twin engine karts there that time, but then Dad was still the fastest of everybody. So even at 71, he's still amazing. Last week they had a thing at the GoPro track here in Mooresville, near where we live, for the Coco 600. They had a legends versus up and coming race at the track, on the rental go-karts. Dad started last, finished first. So, just goes to show, even when you're old, if you got it, you got it, so Dad's doing good for anybody who's curious. And enough of that, let's go ahead and get on with the rest of the program. I want to acknowledge the people that help us with this information. I'm going to be showing a few different things, and some of that stuff is our research, and some of that stuff is research that we've done in cooperation with Oak Ridge National Lab, and some of it's information we've done in cooperation with Afton Chemical. So I want to really acknowledge and thank Derek Splitter and Ashu Gupta for their help in this project. So, it's not just Driven, it's not Lake Speed Junior saying these things. This is kind of a collaboration of people, and we're sharing what we know. So let's get on with it. So low speed pre-ignition, LSPI, is essentially an abnormal combustion event that can cause catastrophic damage to an engine. The piston image right there, you can see the fracture in the ring lands, and that's a pretty common sign actually of LSPI, is that there's the fracturing of the piston below the crown of the piston. It's not burnt. It's not like a traditional detonation event where you're burning a hole through the center of the piston, or lifting, the edge of the piston up. I've done that to myself before, but it's that fracturing of the ringland and down maybe even to the side skirt of the piston, because what's happening is a lot of times with LSPI, the abnormal combustion, the pre-ignition is actually beginning over there in the ringland area sometimes, and that's where why it's showing itself up there in that area. Now there are a lot of different theories as to why LSPI occurs. To date, no one has come out with the chemical equation that says, okay, this is what's leading to it, and this is why LSPI happens. However, we do know the cause and effect relationships. We know that the type of detergent in the motor oil and the amount of detergent in the motor oil has an impact on the frequency and the magnitude of the low speed pre-ignition events. We also have research that confirms that the volatility, the vaporization tendency of the motor oil itself also is linked to the frequency and the magnitude of LSPI events. So we're working through all these things. Oak Ridge, we're actually working on a new proposal that hopefully will get funded, where we can do even more detailed, in-depth results, where we're going to try to do some aging on some oils and see. So hopefully we'll get the funding for that, and we'll be able to do a whole lot more, and there'll be another webinar maybe in a couple of years that really gives you, hey, we found out how it happens. So with that being said, we know what LSPI is, low speed pre-ignition. It's catastrophic damage from a detonation event. So let's kind of get into why this is happening in a direct injection engine and what you can do about it. So next slide, just to, again, kind of summary the previous one, just in a if you're not aware, again, there's a side skirt of the piston blown off. When you have the low speed pre-ignition, you have any kind of abnormal combustion where it's occurring before the spark, what happens is you get super high cylinder pressures. As you can see from the red trace, how much higher the pressures are on the red trace versus the normal combustion. It's those high pressures that cause the damage to the piston. Now, LSPI isn't just a lube issue. And we talked about a few things a minute ago about detergents and volatility, but it's really a very complex phenomenon that comes from the interaction of many different things. And engine design plays a role. I mean, if it's a vertical mount versus a side mount injector, the piston design itself, which we'll cover in the end, the ring package, which we're going to cover in the end as well, those things all have a role. The fuel itself has a big role in this. You can design a fuel that will eliminate LSPI. Problem is that fuel isn't maybe necessarily the best for fuel economy or for the environment, but so there's trade-offs in all of these areas, which is why it's, like I said, it's a complex thing, and why it hasn't been, oh, this is the issue, let's solve it, resolve, done, from a any one perspective, because there's trade-offs when you do things with the engine to solve it. There's trade-offs when you do things with a lubricant. There's trade-offs when you do things with the fuel. So we're trying, as an industry right now, working together. Just last week, I was in Nashville at the Society of Tribologists and Lubrication Engineers Conference, and there was several talks on LSPI and how we're trying to overcome them as an industry. So it's an interesting field right now, and there's a lot of new development going on. So it's going to continue to drive forward, because like we're saying, there's trade-offs, and there's not a magic pixie dust where you can drop it in and everything's just fine. So we're looking at different solutions, trying to mitigate those trade-offs. And I think in the end is we're going to have better performing engines with better durability. And I think we'll end up, in a better place, because we're learning a lot about engines and about combustion and how the interactions of these things are, not just looking at them in isolation anymore. We're looking at these things holistically, which is how we should have been doing it all along, but from the research perspective, they typically look at things in isolation to eliminate variables. But in this case, the only way to really understand it and to solve it is to look holistically. So it's interesting times, excited about it. So again, we're been doing this research, mainly in conjunction with Oak Ridge, but also with Afton and driving Ford, and GM and Ford have a little bit of involvement in it as well. And the platform that we were using mainly was the Ford EcoBoost engine, which you can see there. Just for primer, direct injection means that the injector is in the combustion chamber. In this case, that's a vertical mount injector that's located next to the spark plug. And so when you're injecting the fuel directly into the combustion chamber, that's where things get to be a little bit different. And again, to answer the question that's on the slide, why is it occurring in a DI engine? Well, what we have to do is start thinking about time in terms of degrees of crankshaft rotation. A 4-cycle engine, there's 720 degrees of crankshaft rotation to complete all 4 cycles. And in a traditional carbureted or port fuel injected engine, the fuel is introduced upstream of the intake valve. It's outside the combustion chamber. So, and you think about the piston going down and on the intake stroke and drawing the air fuel mixture into the combustion chamber, there's literally about 360 degrees roughly of time in terms of crankshaft rotation for the fuel to vaporize. And probably now is a good time to really talk about this, that the job of a carburetor and an injector is to atomize the fuel. And atomized fuel is just small droplets of liquid fuel. We don't burn liquid fuel. If you had a 55-gallon drum full of gasoline, you put a spark plug inside the drum and hit the ignition, nothing happens. Take that same drum, take the lid off of it, put the spark plug 2 inches above it, and hit the ignition, there's a huge explosion. Why? It's the vapor that is what's ignited and what burns. So the job of the carburetor in the injector is to atomize the fuel, small droplets. Then it's the heat of the engine inside, it either is the heat of the engine itself plus the heat that's caused by compression that vaporizes the fuel. And then you can ignite it and burn it. So when you look at that and you compare it to a direct injection engine, now with the injector mounted inside the combustion chamber, and to get maximum volumetric efficiency, typically you're only running about half the amount of time in terms of crankshaft degrees of rotation for your injection window. Because to get better volumetric efficiency, while the piston is moving down, you're not running the injector. It's closer to bottom dead center before the injector begins. And so when you have that shorter amount of time to vaporize the atomized fuel, now you end up getting more fuel mixing with the oil. And that's kind of the root of the problem of LSPI, is the mixing of the oil and the fuel. And as anyone that's ever done any sprint car engines or been around any kind of engines that run on methanol, this slide probably looks fairly familiar, that oil and fuel can emulsify. Sometimes they'll separate, like the bottle on the far right. Other times they'll milk up, as we call it, when you see it emulsified, like on the far left. So in this case, we're going from a high calcium oil to a low calcium oil, and it's the chemistry of the oil that's affecting how much fuel the oil can hold. And that's the kind of key thing to keep in mind, because when you start looking at the theory behind LSPI, one of the prevailing theories is that you get this fuel and oil mixing together in the top ringland. Of course, the top ringland is very hot, so now you have this, 2 different chemicals mixing together, and you have the heat from combustion from the piston that is basically acting as a catalyst, and it's creating some kind of either third chemical, or it's at least allowing it to evaporate off. And now you've got this evaporation of the oil fuel mixture, and whether or not it's chemically altered by the heat or not, we're still trying to understand that. There's a lot of research that says yes, it is. It's not just that the oil and the fuel is vaporizing, it's the fact that what combination of oil and fuel that did vaporize has been altered chemically because of the heat, and the temperature and the pressure in the upper ringland area is what's causing something that has lower octane value that ends up causing the engine to knock, to detonate, and that's where the LSPI comes from. One of the theories that's been put out there, and Afton has done a little model, and we'll run this little graphic for you here. That the idea is that as the piston nears top dead center, because of the reduced viscosity of the oil and the fuel mixing together, when you have fuel that's lower in viscosity than oil and they mix together, now that combination is a lower viscosity product. Now it's more easily slung out of the piston ringland area as the piston slows down as it approaches top dead center, and this flying droplet now has this kinetic energy, and its temperatures building because the compression is increasing, and that's what causes it to vaporize, and then that vaporized fuel is what auto ignites. I'm not 100% sold on the whole flying droplet, in terms of it only coming out of the ringland, right near top dead center. I think what could be happening is that, just like, if you go to a NASCAR race, or if you've ever watched a NASCAR race, or pretty much any kind of, high speed race, there's, how does the hot dog wrapper get on the grill of the car? If it's laying flat in the track, how does it get there? Well, hot dog wrapper is laying flat in the track, 100 yards before the car, but there's a wake of air in front of the car that lifts the hot dog wrapper up, and that's what enables it to get caught on the grill of the car. Obviously, as the piston is moving around mid-stroke, it's going as fast as it can. There is a wave of air in front of the piston. There's turbulence in the combustion chamber. I believe it's that turbulence that's probably lifting that reduced viscosity oil fuel mixture out of the ringlands and all that. It's not necessarily the slowing down of it, but I think it's probably more the turbulence that's doing, but that's just my theory on it, and who knows what I know. So anyway, that's the one theory, is that, and obviously when that goes off, this theory that the droplet, however it gets there, that the droplet vaporizes, and because the octane value of the oil is lower than the fuel, what happens is you get detonation. And we kind of were able to prove that out by looking at the different volatilities of different base oils. So what you're looking at here on this chart is the base fuel, the line in orange. That's a base 93 octane fuel. As you can see, that your R plus M divided by 2. And the RON and the MON are your research octane number and your motor octane number. Those are the 2 octane tests they run on all fuels. So now you're looking at the base fuel plus a 25-to-1 ratio of PaO2, which has a very high volatility. That NOAC of 99 means that 99% of the oil will evaporate in 1 hour at 250 degrees Celsius, which 250 degrees Celsius is about 500 degrees Fahrenheit, which is what they say the underground temperature of the piston is. So basically you're approximating, okay, this is a very high volatility oil, and you can see that it has an immediate impact of lowering the octane from 93.4 down to 91.4. So that's going to lower the octane, increase detonation for that specific engine by having that high volatility. When you drop down to the U base 4 and the volatility drops from 99 to 13, now the octane only drops from 93 to 92. And you go a step further to the even lower volatility base oil that's 4.6 on the NOAC scale. Now the octane only goes from 93.4 to 93.1. So we can see that there's a definite correlation between the volatility of the oil and the effect on knock and detonation, pre-ignition in the chemistry. So the base oil certainly has an effect. Volatility is a big driver in that, but the additives also have an effect. So we studied in the project with Oak Ridge every different additive that goes into a motor oil. We track different levels of calcium, magnesium, zinc, moly, tungsten, sodium, pretty much every additive you can put in the oil. We tried it at different levels to see what the impact was. And we used, production lubes off the shelf. We had all these different, research numbers We did over 115 different formulations to figure out what was going on. So it was pretty intense work there for a while. Did some testing, and what it boiled down to was essentially the higher the level of detergent, specifically calcium and sodium, the higher the tendency and magnitude of the LSPI events. You know, the great part of working with Oak Ridge, you know, is they're a government agency, so the government pays for everything, which is not a bad thing. The only downside of that is they're a government agency, so they move at the speed of government, which is not quite as rapid as we're used to in the racing environment. So, you know, it's funny with, you know, we showed the picture of the 3.6 liter Ford modular, the injector earlier, and when we were doing some of the early testing, you know, they turned the boost pressures up and tried to really study what was going on. Of course, we ended up blowing the engine up. You know, you get enough LSPI events, it destroys the engine. Well, you know, the government, they only give out money every so often. They're not, you know, sending out checks to the research labs every 2 weeks. So the funding comes quarterly. So if they blew the engine up, you know, a couple of days into one quarter, you have to wait, you know, 3 more months until they get money to go do it again. So we got a little bit impatient. We went out and bought our own direct injection engine, the LT1 that's pictured right there, partnered with Ben Strader and the guys at EFI University, because, you know, I come from that, you know, go-kart background. I'm a carburetor guy. You know, most of my life in NASCAR was pre-fuel injection. So I'm not an EFI guy. Ben's an EFI guy. So working with him, you know, using HP Tuner software to be able to data log the knock events in the engine, we had a pretty good tool to actually start studying the effects of these oils in a real engine on the dyno. And what we found out was when you had different combinations of calcium and sodium, which tend to cause LSPI, and then molybdenum, which actually can reduce LSPI. We played around with some different oils. So oil A was a mixture of half calcium, half sodium detergent. And when we ran our test, we would idle the engine for 5 minutes, make a full hit, idle the engine for 5 minutes, make a full hit, idle engine for 5 minutes, make a full hit. Did that several times, and over that piece, we actually had 5 knock events over that series with the calcium sodium mix. Then we went to a only calcium, no sodium, but it's a very high level of calcium in line with the traditional API SN and the European ACA A3 B3 spec. With a little bit of moly in it, and it still had 5 knock events. But as soon as we lowered the calcium level down to 1,500 parts per million and kept the moly right where we had it before, all the knock events were eliminated. So just by changing the chemistry, the balance of the additive package, we were able to, in the LT1 engine, eliminate any kind of knock retard going on, any kind of detonation events happening because of the oil formulation itself, which that all correlated exactly to what we were seeing with the testing at Oak Ridge. And what's interesting, around the same time, our European distributor, which is also the Sunoco fuel distributor, called us up and said, hey, we're having a problem with the Mini Challenge. So as you can see in the picture there, the little Mini Cooper, the Mini Challenge is a 1-make series, and those are all turbocharged, direct injection, 4-cylinder engines. And they went to a control fuel so that people wouldn't be cheating with the different kind of fuels they were running. And they started running the new control fuel, and right off the bat, they're actually blowing up engines on pit lane. They're looking at the data logger, and there's knock going on all over the place, and it's the worst leaving pit road. And they failed a couple of engines, and of course, they're saying the fuel's not right. These are big issues, and the Sunoco guys are getting involved, and they're looking at it. And the Sunoco guys called us up and said, one of the engineers at BMW said something about maybe being a low-speed pre-ignition. Do you know anything about that? I'm like, yeah, actually, working on a project with Oak Ridge. I asked them, what oil are you using? And they told me what type of oil it was, and it was a European spec oil where the calcium level was about 3,000 parts per million, and there was 0 moly in it. I said, okay. I said, these are just race-only cars, right? They're not driving on the street. No, it's race-only cars. Okay. I said, why don't you put in some XP9? because they were running a 0W40 Euro spec oil, 3,000 parts per million calcium. So when you go to XP9, you're going to maintain that 40 grade, but you're going to go from 3,000 parts per million calcium down to 300 parts per million calcium. And you're going to go from no moly to 1,000 parts per million moly. Put that in, go see what happens. They put it in there, all the knock is gone. The data logger goes from looking like, a bee's nest of activity down to just calm seas. And they eliminated the engine failures. They went on, everything's good. They're super happy with the oil because, not because it's anything special necessarily. It's that it's the right balance of chemistry for the application. That turbocharged direct injection engine, especially in a race situation, with the engine a little more tuned than a factory setting, it's creating more load, which is, pushing the engine closer to knock. And then the calcium package in that road spec oil was exacerbating that problem. And by going to the XP9, the lower detergent formulation, that's what fixed the problem. So that was kind of fun to see a real world example of that. So, that we've got all the theory going on in the lab testing, and we saw some dyno experience. And then with this, we were able to see real world on the track experience with these things. And what it really all boils down to is that the additive package is what really matters. That's the thing that has the most impact, that calcium and sodium content tend to increase LSPI. Magnesium is neutral, and then higher levels of ZDP, higher levels of moly actually decrease LSPI. So that's one of the challenges for the industry, is that, we've been on this old bandwagon, reduce ZDP, reduce ZDP, reduce ZDP. But when you turn around, you look at a DI engine, well, you kind of need ZDP. It helps. So, well, moly will probably be the one that probably carries the day, because moly can do the same work that ZDP does. And so you're probably going to begin to see oils with more moly in them in order to help, mitigate this and create that correct balance we were talking about. A good example, and we've seen this in the last year or so since we started talking about this, is, a pretty common thing is, a guy has this 2016 Camaro with an LT1 engine in it, and he decides he wants to put a supercharger on it and long tube headers and tune it up, and he's going to go the drag strip some. Well, now that in his mind, he's got a race car. So what does he do? He goes down to AutoZone or wherever and grabs some racing oil off the shelf. The problem is the racing oil off the shelf at AutoZone has a ton of calcium and a ton of sodium in it. And so he puts it in and it has LSPI and blows the engine up. So that's where, traditionally what we've had on the shelf for racing products, and even this, regular European products and diesel oils, are the same thing. So it doesn't have to be just a racing oil, but what's been on the shelf traditionally has been high calcium, which is going to be a problem for DI engines, especially boosted or tuned up DI engines. And that's why, DI formula oils are going to contain less calcium. You can see the two, darker blue bars, the higher the bar, the more calcium. Lower the bar, less calcium, and that's what you want. You want more of that balanced package where the amount of calcium and the amount of zinc and moly together are about equal. That's where things tend to be happy. And when you have them out of balance, like you see on the right, that's what ends up kind of increasing this tendency. And like I said, but it doesn't matter if it's a diesel oil, it's going to do the same thing as this racing oil that's off the shelf, or even a Euro spec oil. They're all going to create that same kind of issue. And so what's happening is the industry is in a state of change right now. Last May, API SN Plus came into effect, and it's making its way onto the shelves over the last year. And the API SN Plus does address some of the low speed pre-ignition problems. It's running the sequence 9 test, which is the new test for low speed pre-ignition. And when that happens, they're reformulating the oil. So when you see an oil that's got API SN Plus, that logo up there on the left on it, then that's an oil that's been reformulated to change that detergent balance to try to make it work for LSPI. GM has the Dexos 1 Gen 2, which has got to be that exact logo. And that was introduced in September of 2017, and it's out there pretty good now. And those oils have been reformulated completely from the ground up to address not only the LSPI issue, but also the soot that's created in direct injection engines. Just like diesels create soot because of that late injection, DI engines also create soot, and that can cause timing chain wear and some other issues in the engine. So, the Dexos Gen 2 spec, or Dexos 1 Gen 2 spec, covers both LSPI and soot wear, whereas the current SN Plus only covers LSPI. It does not address the soot wear, in that package. They are working on something to replace it that will, but it's not done yet. From our perspective, we've been fortunate from Driven side to be able to be involved in all this research for several years. So we kind of learned what works and what doesn't work. So we came out with our own line of DI formulated oils that are like the Dexos 1 Gen 2 spec. They're formulated ground up to address low speed pre-ignition and soot wear. And the one nice thing about the Driven line is we cover everything from 0-20, 530, 0-40, 1550, 1060. We cover the whole game, whereas the Dexos 1 Gen 2 spec only covers 0-20, 530, and 0-40. So we got a little bit wider offering now, which is kind of nice. But again, that's the good thing, is that as consumers, as engine builders out there in the marketplace, today you have options that you didn't have, a year or 2 years ago, which is good because these engines are real and the problem is real. And now there's some tools you can use, options you can have to try to mitigate that risk and get better performance. Now, if you kind of look at the history of this, I think this is kind of a fun slide. Again, the blue bars are the calcium. And you look back at the very bottom, that's API SN before the change last year. The original Dexos Gen 1 spec. Then the ACEA, the A3B4, that's a European spec. Look how high level of calcium those oils are compared to the current SN Plus and the Dexos Gen 2 and the Driven DI line. So much less calcium than the other oils. And you have a higher level of moly as you come along, and that moly is really what helps provide better wear protection, as well as reduce friction, better fuel economy, better horsepower. All those things kind of roll together because of that higher level of moly. Now the fun thing is we're not done yet. We're continuing to do research and work even with the current funding we have. Again, hopefully we're going to get some more funding with the Oak Ridge guys to be able to do more research in the future. But this was a kind of a fun one that Freddie Terza and the guys at the VP Racing Fuels helped us with last year, is that if you look at the fuel effect, we mentioned that earlier, the fuel has an impact on this. This is the distillation curve of two different fuels. So you got VPC10 and VPC20. So that vertical axis is temperature. The horizontal axis is percent evaporation. Remember we talked before, you can't burn liquid fuel, you can only burn vaporized fuel. Well, because a fuel is a blend of multiple molecules, they don't all vaporize at the same temperature. They will begin to vaporize at one point, and then over time and temperature, the rest of it vaporizes. So the blue line is the distillation curve of VPC10, which is a 100 octane fuel. And then the orange line is the distillation curve of VPC20, which is a 98 octane fuel. Now, you'd think that the higher octane fuel would obviously have less knock, but at 120 degrees coolant temperature, so pretty cool, right? But think about it, for a lot of street cars, wintertime or whatever, you get out there and crank up, start driving around and get at the stoplight, let the car idle a little bit. It's pretty easy for the temperature to be around 140 degrees Fahrenheit coolant temperature. At that low coolant temperature, the C10, the higher octane fuel, would knock, whereas the 98 octane fuel, the C20, would not. And the reason for that is the distillation temperature. You can see that it's much flatter. So at a lower temperature, by 225 degrees, 100% of the C20 is evaporated. But at that same temperature, only 50% of the C10 is evaporated. So, a couple of things there. Obviously, when the heat of vaporization, the cooling effect of vaporizing the fuel helps bring down the combustion temperature, which helps, reduce the tendency of knock. So that's a big part of it. But also too, just the fact that with the fuel that's not vaporizing, you're also getting more fuel dilution in the oil, and you're now being able to kind of, get those other parts of the LSPI piece, kind of fired up, if you will. So that's one part of it. Another thing I want to share with you, and this is the guys at Jasper Engines and Transmissions allowed us to share this information. They rebuild the Ford 3.6 liter EcoBoost engine, and they offer a 100,000-mile warranty on it. And they can't really decide and make people run a certain oil. So they had to design the engine to run 100,000 miles with whatever oil they're going to throw in it. It could be high calcium oil. And their answer, as you can see from this picture, is they really redesigned the piston and the ring pack in a fairly major way. So the OEM, the Jasper piston is on the left, the OEM piston is on the right. And what you can see is they moved the ringland down on their piston. They added an accumulator groove, and they changed the ring pack. So they did all these things to get better oil control, to try to keep the temperature, the temperature of the oil fuel mixture, make it lower by moving that ringland down and get a little better oil control. And then also you can see here too, under the bottom of the piston, the OEM piston has got 4 drain back holes versus 14 drain back holes in Jasper's piston. So by having more drain back holes was allowing more of the oil to get out of the ringlands. That way you weren't trapping as much oil near the top of the piston, where it could get more fuel intrusion, where it's hotter, where that cooking effect, is taking place. So this is a really great mechanical example of how you solve the problem, but it also sheds some light on what's happening chemistry-wise. When you have more drain back holes and you move the ringlands down, what you're doing is you're getting more oil out, and you're reducing the temperature of the oil, and now they're not seeing the LSPI issues with the same bad oil as you did with the OEM piston. Now, does that package have as good a fuel economy? No, it doesn't. Because it's that you're going to get a little bit more emissions because the ringland being down, the crevice volume is going to be a little bit higher, and then you're going to have a little bit less fuel economy because of the higher ring tensions and all that. So there's trade-offs, like we mentioned before, and that's why there's no simple answer. But these are all good things that kind of illuminate the subject and let you kind of have a better understanding of what's going on, as we move forward and try to really figure this thing out and, make things better for everybody and build better engines that are more durable going forward. So, and kind of in summary, the low speed pre-ignition is an abnormal combustion event that can be catastrophic to the engine. Here's a great piston image that was given by one of our customers after we gave them one of this talk. They said, "Oh yeah, everything you said happened to me exactly." And that's the result of it. Ongoing research, the droplet formation is the piece, the volatility of the oil, the detergent package, specifically calcium and sodium. And one thing about the calcium and sodium I didn't mention earlier is that, sodium pretty much has if it's there, at any kind of significant level, it's going to cause a problem, which is why sodium detergents are pretty much being universally eliminated across the board. The people that made sodium detergents are not going to be making sodium detergents anymore. So there's going to be some changes to some oils out there that have traditionally used sodium detergents because they're going to go away. It's not the oil company's fault. It's just that, the sodium detergents are bad for LSPI, and the main market is passenger car oil. So you're going to lose that detergent. So that's going to cause some changes in the industry. But the calcium relationship, as you can see from the previous slides, if you kind of picked up on it, it's not a linear relationship. It's not like, there's X amount of LSPI events for 500 parts per million calcium, and it's double that for 1,000, and then it's, triple that for 1,500. It's actually very much of a hockey stick relationship where, from 500 to 1,000 to 1,500, you're seeing nothing. But then when you get to 2,000, it takes off and goes vertical. And 2,500, it goes even higher. So that's why you're seeing even, these oils are out there now, the SN Plus, the Dexos Gen 2, our oil, they still have, 1,500 or so parts per million calcium. And we're okay with that because that gives you the detergency to keep the engine clean, the acid neutralizing ability that you need. So the sodium, the detergents are there to do a job. And You want to have enough of them there to do the job well. But then as you add in things like MOLLE and the ZDP, you can balance out that to make sure you've got a good margin of error to protect the engine from LSPI and still have the wear protection you need, still have the detergency you need. So that's part of this whole thing, is that, you know, as a formulator, it's exciting because we're working on things and we're really learning moving these levers and making better oil. So things are going to continue to move forward. We're going to continue our research. The industry is going to continue its research, and then there's going to be more changes coming in the future in the industry in response to all of these things. So with that, I think I left this up about 15 minutes so we can have some questions. If anybody has any questions.
Sure. No, thank you, Lake. That was a great presentation. And it's like we talked about earlier on the tech line, we're also seeing these failures come through, and we're starting to get questions on it. So you're creating an awareness out there of what LSPI is, and we really do appreciate that. So because we are seeing it come through the tech line now. So we do have some questions for you.
Okay.
First one, has LSPI been an issue with cars equipped with direct and port injection? So example, the Subaru FA20 engine.
Yes. So anything that is direct injected at all, even they call them the dual fuel, where you have both port and direct injection, it's still a problem. It's not as big of a problem with a dual fuel system, because a lot of times the engine management system switches and runs on port injection in the temperature and load combinations that the engine mapping says, hey, this is where LSPI is most likely to happen. We're going to run the engine on port injection in these areas. That way we reduce the risk. And then we'll switch back over to direct injection when we're out of the danger zone to be run more efficient. The problem is, we've been saying it's LSPI, low speed pre-ignition. At the SAE World Congress back in April, it was kind of established that we're not going to call it LSPI anymore. We're going to call it SPI, stochastic pre-ignition, because we're seeing examples of this pre-ignition at other combinations besides low speed, high load. That we're seeing it at higher engine speeds and lower loads. So it's a bit of a random occurrence. So that's why we're saying it's not just because you're dual fuel doesn't mean you're out of the woods, because we're seeing it more broadly as more and more engines are out there running GDI.
Okay. Here's a really good one for you. Considering more DI engines are hitting the inboard marine industry, what kind of impact could LSPI have on the marine industry, especially considering how boats are driven from idling to all out?
Ooh, yeah, that's. I think there's a high potential for problems there. I say definitely, because boats run in a cooler environment in terms of engine temperature, typically because of the availability of cool water in a marine application, and the fact that they do run at typically very, very high loads. A lot of times idling at low speeds. I would think that as you get direct injection engines going into marine environments, the chance of those problems are much greater. And that's where things like engine mapping are going to be really important, fuel quality, and obviously the oil choice is going to be paramount. That's going to be the first thing the consumer can do to make sure that they're not putting themselves at a higher risk of problems than are already innate in the architecture of the engine.
Okay. Another question is, does the driven DI line help reduce soot as well?
No oil reduces soot. The soot is a byproduct of fuel that is not vaporized. It's the carbonization of unburnt fuel. But what can the oils how they handle the soot, and can the oil prevent the soot from agglomerating and creating wear? I mean, soot's just hard carbon. So diamond is hard carbon. So when you have a high level of soot in the oil, it can cause abrasive wear. So the driven DI oils utilize a couple of different chemistries that are designed to reduce, soot wear, and they do it quite well. So that's how we handle it.
Okay, all right. Will the ZDP and moly with reduced calcium formulations have any effect on carbureted engines, positive or negative?
When you reduce the amount of calcium in the oil, you reduce competition with the ZDP and the moly. So now the level of ZDP, the level of moly you have in the engine for anti-wear is more effective, which is what we've been doing with race oils all along. That's the main difference between a race oil and a passenger car oil typically, is not the amount of ZDP or moly. I mean, yeah, you can add more, but what's more effective is actually having less detergent in the oil. Where a race oil maybe only has, like I said, 300 parts per million calcium, whereas an average passenger car oil used to have close to 3,000. Of course, at 300 parts per million calcium, you can't live very long. The oil is short life, which is what you've seen with race oils, and real race oils in the past are all low detergent. What I think you're going to see is, as the calcium levels come down, the sodium is eliminated from off-the-shelf oils, I think the wear protection is actually going to get better. And that's for the first time in probably 2 decades, off-the-shelf oil in terms of wear protection for performance engines and race engines will actually be better than it used to be. Now, I'm not saying it's going to be sufficient to do A+ work, to give you the best possible protection in a performance engine or race engine. The detergent zinc balance still won't be optimized because there's a limit on how much zinc you can put in the oil. Those zinc limits are still in place, so it won't be optimized, for a race engine or a performance engine, but it will be better than it has been, because as you change that detergent balance, you're changing the balance of the chemistry on the surface, and you're allowing the zinc to do a better job. I think I answered that question. Maybe I didn't.
Okay, no problem. In your experience, does retarding the spark timing seem to give more time for LSPI to occur in a combustion cycle?
It can actually, yes. That was one of the interesting observations from some of the combustion work. I'm not a combustion PhD. Derek Splitter from Oak Ridge is, and that was one of the things that he found, is that when they delayed the spark timing and you gave it more opportunity from a time window to pre-ignite, it tended to do that, yes.
Okay, all right. So I know you touched on this one just a little bit already, and you mentioned, so, really, what's your opinion on the status of what's on the shelf today in regards to oil? What do people need to be checking with their, with the people that are servicing their vehicles to make sure they're putting in the right oil? Like, really, what is your take on that?
Yes, I mean, I'm a kind of person that I change my own oil. I don't go to quick lubes, and but over half the market is quick lube, and quick lubes typically use bulk oil. And the bulk oil is typically, it's on spec at least 80% of the time according to the API, but it's the lowest common denominator. And so with the API SN Plus out there now, been out there for about a year now, I would guess that most of the quick lube tanks have been now started to switch over to that. I don't trust the bulk oil in the ground as much as I do the packaged stuff. So if you're going to a quick lube and you have a car you really care about, that's not something that you're leasing and you don't care about, I hate to say it, but it's true, right? That's what changed the whole automotive industry, is that people started leasing cars as opposed to buying cars. And so the maintenance and the care and the thought and the passion for the vehicles all change when it's not yours long term anymore. Just got to call it like it is. But if you got the car and you plan on owning it or care about it, I would make sure you have them use the oil that's either in the bag in the box or that's in the bottles, because that oil tends to be more current spec, closer to being on quality. And I'm talking about this in a daily driver aspect. I'm not talking about a performance situation at all. That you really want to make sure with today's technology and how diverse it is that you're getting the correct viscosity oil and the correct spec of oil for your engine, for your transmission, for your gears, because they're right now in the marketplace, because of the fuel economy and the emissions standards that are being imposed globally, not just in the US, but globally. There's a proliferation of diversity. There's people trying to figure out what's the best way to attain better fuel economy, to get better emissions. So you've got 8, 9, 10 speed transmissions. You've got direct injection. You've got hybrids. You've got series parallel, series and parallel hybrids. So you've got a lot of different things in the marketplace, all of which are their own unique application. And each of those applications needs its own chemistry to make it perform at its best. So that's why it's important right now, more than any other time, and I can remember in history, that it's really, you got to look at your owner's manual, really see what the spec is, viscosity, and do that. And then obviously when it comes to racing, it's the same kind of situation. You really need to be doing your homework and figuring out the application, letting the application dictate the chemistry, and then going from there. I think in the future, the winner of what is the best way to do this will become clear, and you'll see a gradual reduction in complexity. There'll be less diversity, more commonality at some point in the future. But for right now, things are going to be very diverse. Next year, API SP, the GF6 spec will be coming out. So that will be another change. Hopefully that'll be an upgrade from where we are today, but you don't know yet. It's unknown what those oils are going to be, but we do know they're coming. So SP is coming next year. What comes after that, the European specs, they're trying to get those changed as well. I don't know that GM is going to make any changes to the Dexos anytime soon. They got their act together first and got their testing done. A lot of people were kind of negative about GM coming out with Dexos, which is just their spec. It's not a brand of oil. It's just their spec. And people were negative about that. So they were money grabbing. Well, guess who got the job done first in terms of addressing low speed pre-ignition in DI engines? They did. Why? Because they weren't beholden to anybody else. They weren't tied up in a committee of other manufacturers and oil companies trying to figure out the situation. They just had to worry about their engines, and they figured it out and got it done. So another good example of fracturing of how things have been done traditionally. But in some ways, that's not necessarily a bad thing, because in the end, it leads to a better solution, which is better for the end user. So it's exciting times because of all the change. And I think good will come from all of this change. You just got to be aware of the fact that things are changing, and just know that things are changing, and don't just think that it's not.
Yeah, no, true enough for sure. And like I say, on the tech line, you've created an awareness with what you're doing, and everybody out there now at least has some answers to what they're seeing when they take things apart, especially some of these later engines. So we do appreciate that, Lake. I know there's more questions here, and what we'll do, everybody, is we'll get those over to Lake for you. I would try to cap it at just about an hour for the presentation, just so that everybody can get on with their day. And no questions will get unanswered, so we'll get those over to Lake. And Lake, we want to thank you very much for the presentation today. Your stuff is always just a real eye-opener, so thank you again. And from all of us, we do appreciate it. And
I appreciate it, Rob. You and Amanda, yeah. Steve, and everybody, at AERA, we appreciate what you guys do for the industry, and we're happy to help how we can.
Yeah, no, super. And like I say, if anybody got any questions for Lake, you just go ahead and email us. We just put up a slide there that shows our contact information. Amanda will tell you how to fill out that survey. We'll get her back on. And again, any questions, just fire them our way and we'll get you looked after. So thanks again, Lake, and you have a good rest of your day.
You too. Thanks, everybody. Bye-bye.
Thank you. Hey,
All
Amanda.
right, you guys. Just a couple quick things here. When you leave, there will be a survey that pops up. Please take a moment and fill that out. That just lets us know how we're doing and gives you an opportunity to ask any additional questions you may have. Also, tomorrow you will see a link to the recording of today's webinar, and that is yours to use as you would like. You can share it with people on your staff. You can watch it at your convenience, whatever you would like. Other than that, as Rob said, you can see our contact info there. You can also respond to any of the emails you get regarding the webinar, and those will come straight to me, and we'll get your questions answered. So thank you again, everybody. We appreciate you taking time out of your day, and we hope you have a great rest of your week.